recording. And now through Teams, I'll share my screen. Jeez, let's share entire screen. Okay. So I hope you can see my screen. There should be a secure presentation. So if I just play from start, then it just becomes yeah, please speak. Sorry. I thought your hands was up.
Yeah, my hand was up to say that I see the screen. Sorry.
Okay, thank you. So if I click this, yeah, thank you. So if I click this play start from button, then it just splits my screen in something else. But so I'll just not do that. Anyway, it's the text important, that let's just leave the cosmetics out. So when we talk about CQRS, actually it stands for Command Query Responsible Segregation, but it's actually somewhat you would see a little bit big commitment. Maybe it's an architectural pattern. And then for people who want to go a little bit gracefully, actually it evolves in some steps. So the first iteration might be command query segregation. So that's just, it's like a standard web application, but what you do is, let's say you have an API, you just separate your API, the surface of your API, with commands and queries. This is very, very standard. But your model stays the same. Whereas CQRS, if we go with the second phase, this is how I start my project. I still decide I'm not sure if I commit or not. But with CQRS, you also separate your models with command model and the query model. And then the third iteration would be to apply on event sourcing. Event sourcing is about composing your system set of events, such as if you take your bank statement, you will see there's some sort of plus minus transactions. We somehow convert our system into that kind of set of events with CQRS. In some way, when you do function programming, CQRS with event sourcing is very well matching with functional style, because we don't want objects floating around. We just want to communicate via messages and then events and commands. So in this presentation, I'll just try to address, I hope it's not so small, slides are, 3 aspects of it. So what is CQRS? Why do I care? And how do I use it? So let's just start with what CQRS is. I made a brief intro already, but let's just make a little bit more concrete definition. So you heard this command query segregation. Make yes, I do share my screen. Is there anyone who can't see my screen? I assume, but I'll try rejoining. Yeah, people do see. There's a command side and the query side. So what we call this command is just the definition is very important. So I'm just talking, but command is something you describe. It describes a request that you make. So let's say you want to add money or you want to transfer money. So it represents a request, but that request needs to be validated and it's not guaranteed that it will happen or not. In some sense, a command is something that represents a demand to alter the state, and it doesn't return the state. Whereas a query is like I'd like to know what's going on in the system, so it just returns data or state, but it doesn't alter it either. So you're not allowed to change your state. In other representation, we can represent CQRS as in here. So there are two components. One is a command handler and this is the event handler. So initially, whenever you want to, for example, transfer money, you issue a command to this command handler, and you get the state. What could be the state? Perhaps your balance, your current balance would be your state, right? So if I want to transfer money, I need to validate if there's enough balance. So the command and state comes, and the command handler checks if there's enough balance in the account, and then it comes to a conclusion. One conclusion is, say, well, this transfer, for example, this transaction succeeded. The other conclusion is this transaction failed. Maybe there's not enough balance or something else. These two transactions succeed and this transaction failed are the events. So notice I use past tense for the events because they represent something already happened. It's not something I demand anymore. And once those events come up, we publish to the system simultaneously. We apply them through event handler. An application, by applying means, so we have an event handler. This gets the event. Let's say transaction succeeded. It gets the state. Let's say we have $100, and the event says in the event details it's written how many dollars we are trying to deduce, and event handler decides the new state. In this case, it could just subtract the amount that is written in the event from the current state, and you end up with $90 if this transaction is about $10 deduction. So that's the infinite loop of events CQRS actually in another aspect. Whereas architecturally it looks like this. So you have, for example, some sort of UI, a typical web application, and the query, and there's a query model and the command model which are separate, and then these things talk to the database. The distinct thing is, I will reiterate this over and over again. Why bother? So what is the advantage of CQRS? Why do I care? You would, if you search this from Google or other search engine, you may see a lot of different answers. Some people say it's performance, asynchronicity, etc. It scales better, but these are all side benefits actually. If you were to ask me, the real benefit and the actual real core benefit of CQRS is once you separate your command model from the query model, your command model, which is the core part of your application, is protected from the changes that is due to the query model. That means just because your boss wanted some different query or wanted to see a different data, you don't have to go and pollute your command model. Even, for example, you could just make these things deployed into different microservices. And then you could just deploy the query model, updates to the query model without endangering the system. Because every time you make a change, you're potentially introducing a bug, right? And our most valuable logic is in the core model, which is in the command model here. And our ultimate goal is to touch there as little as possible. So that's the real benefit of CQRS. The other things you would hear is the side effects, side benefits such as the asynchronicity, eventual consistency, etc., etc. Next slide is also same. It's a little bit more simplified version of the same thing. Whereas on the left-hand side, you see a typical application people used to develop. There's just horizontal layers, and the traffic just goes on up down. Whereas with CQRS style, then you separate your core part into commands and queries, and then they don't have to even share the same database, these parts, which we will see briefly. So this is another representation of and it's actually with event sourcing. So what you do is there's some sort of set of set of commands come and then they generate events, and these events are stored in some sort of event store. It could be a database, a simple relational database, or it could be something like, I don't know, MongoDB style or some sort of log style thing. And there is some sort of a projection manager where it constantly scans these events from the log of events and then creates the reporting tables. By reporting, it's not necessarily for reporting, but whatever you need to read, that's where it goes. So as you might guess, this introduces some discrepancy. So by the time these events happened, you commit the events, the left-hand side will say, I'm okay, I'm committed, I've done what I did. But at that time, it is possible you may try to read the data from the read store. You may encounter with some sort of stale data. So that's something you should be aware. And that's what scares people, actually. As a developer, when I say typically, hey, I commit, I'm done, I should be safe, right? And that's where things are different in CQRS. It just initially you feel a little bit less confident about the system. But it's actually widely adopted, perhaps to a degree. This is some of the videos. Probably there won't be any sound. I'm not sure if you will hear. I was working in Dubai for immigration systems, and this is something world's first smart tunnel where basically a passenger, whenever they need to exit the country, you need to scan your passport, etc., to the officer. In many countries now, there are automated systems where you scan your passport against a machine, and then the machine just lets you go or not. There's a little bit more advanced version of it. You don't even show your passport. While you just walk through a tunnel, and that's it. You don't show any documents. You don't show any passport. While you're walking, the device has capability to scan your eyes and find out who you are, and then complete your immigration process on the fly. This device is still there. I completed this project in 2020. And if you go to Dubai, it's world's busiest airport, by the way, by the international passenger traffic. In the business hall, which is actually quite expensive. It's there. Can I play it here? Okay. So you may not see. I'll just cut down the audio. So there's just something, but I just want to show it in action. So you see, this is why I'm showing this, because this is some project. It's a mission critical project, which is something I completed based on CQRS based architecture. So it's talking, it's great, it's fast, etc., etc. So just a real life application of it. You just walk and done. But there's an officer monitoring your status. Of course, if you fail to pass for some reason, maybe you committed a crime, then they will stop you. They won't let you go. So while CQRS is nice, I would suggest you don't have to commit yourself. I'm not saying that, hey, drop all your code. And from now on, you will write CQRS. It's not like that. Typically, what I like in an application, I like to split into vertical layers, not just horizontal layers. They are like bounded contexts, if you're familiar with domain-driven design, whereas the left-hand side is the authentication, for example, in this example, transactions and contact. Perhaps you can pick a vertical slice and do it in CRUD way. Perhaps another slice you can use an ORM, and perhaps only one of the slides you could choose CQRS. And this way, and probably I would choose the most valuable, most complicated part. And probably this way you can just accommodate the complexity of CQRS. Any questions so far? So this is how otherwise I'll just move to part 2. As a recap, so CQRS stands for Command Query Responsible to Segregation. A command represents something that's needed to be, that's a request, and whereas event represents something that's happened. The main benefit of CQRS is just separating the command and query model. And we also have event sourcing, where we store the events in it like a ledger database, and that's the essence of it. So why should I care? So I already gave the answer for the question, which is it protects your domain. But let's just talk a little bit more in detail for this thing. So suppose that you have a database at users, and this is a very simple thing. You have an ID, primary key, something like that, username and password. And this is in production for some while. At some point, your manager comes up to says, well, there will be a security audit, and would like to know how many times users change their passwords. Well, you don't have that information at all. So your once you come with this request, whether you like it or maybe it's a silly request, that's another story. I admit it's a bit contrived example. The initial developer reflex is to add a column here. Okay, so you can just add a column here. But once you add this column, then, well, if you use an ORM or some sort of data model, what you need to do is you need to propagate this thing, right, into your model. So you need to add a property or the domain or your data model, and then you need to map this. And then, well, once you do that, you need to deploy this. And who knows, maybe you'll make a mistake. And it's not all. What if, so then as a developer, I would, if someone comes with this request, my initial instinct says perhaps they would want to know between some data intervals, they want to take that report. If you model this, you're not going to answer that query, because if they, well, how many times a particular user changed their password in the last month, you can't do that. Then you're just inclined to obviously create a log table kind of thing. Then and maybe you'll just try to put there every time a user passed, and then the reporting will be based on that table, which is you're a little bit more towards CQRS style actually. But why don't we have it in the first place? So in a CQRS based style, you basically record everything happens in the system, so you never lose any data. I mean, in a hypothetical case like this, if your boss comes with something that you never thought about it before, right? There's a good chance if you go with CQRS with event sourcing, you already have the necessary data. It's just you don't report it, and that makes your life far easier. So in another aspect, the event sourcing is you can see it's like a set of events. So you have order, let's say order created, order updated, order pending, etc., etc. By the way, the terminology is somewhat wrong here. I would always recommend use proper domain language. You don't create an order, you place an order. So that's better. So I would try to refrain this created, updated stuff as much as try to use more regular language. But anyway, that's another detail. So basically, then what we do is we bookkeep what offset. Whenever we create a projection, we bookkeep what was the last event we processed, and then we continue to project it. Which we will talk about a little bit more in detail for the implementation part. There is a second great benefit of CQRS, in particular with, now I'll start talking about actors. So it's another way to, how are you going to implement this? It actually handles concurrency very well. Well, your application is meant to scale, but let's just talk about some of the potential problems with concurrency, which is very, very underestimated. So this is a source code from GitHub. I think it's a to-do MVC with ASP.NET. It's written by maybe famous ASP.NET architect David Fowler. It's a little old edition. So can you see what's potentially wrong with this? It's not something very wrong with that, but there's at least an annoyance for me. Can you guess? Any ideas? Okay, that's reasonable.
Someone,
yeah, please speak.
Someone could create a to-do by the time this code gets to the save changes.
Yeah, that's true. Yeah, that's true. I would also say someone can just delete it by the time you're trying to update it. Then
oh, sorry, this is an update.
Yeah.
Okay.
And then you say to the user, I updated it, but it's not updated. That's a lie, right? It's actually deleted. So it actually doesn't handle concurrency, and it's not his fault actually. First of all, this is a very gross simplification of a demo application, and secondly, at that time the tool handling the concurrency is somewhat very challenging. Actually, it's not as easy as you might think. So in a later iteration, because he's a smart guy, he fixed it by using the Entity Framework 7. And so Entrepreneur 7 offers another thing. So you could just do in-place updates or in-place insert, where there's a switch called execute update async, which issues an update command directly. And because he's a smart guy, he also checked this time how many rows affected. So when you issue an update command, the database is usually, relational database usually also tell you how many rows changed due to this thing. And if no rows changed, then please mute. Yeah, thank you. If no rows change, then that means something deleted. And then obviously he responded more better. He gave you more better answer that's not found actually. But there's a possibility. Please mute. Someone is unmuted. And yeah, I'll mute you for you. Thomas, please mute. Okay, I'll mute it. So basically, this way, you could just solve the problem, but it still doesn't guarantee. Actually, it's possible that after you commit it, update is successful, it could be just deleted. You can say, well, there's nothing we can do about it, right? Perhaps, but it is possible that the one user wanted to be deleted. It's somewhat a different version of the application. Perhaps, I mean, the person who was deleting it, if they would have seen the updated version, maybe they would have rejected the idea. Maybe they wouldn't have deleted. We don't know that. We can say, it's concurrency. I have only few users in my system. I work for a small shop. I don't have this kind of problems. This is for the Google-like companies. That's not true. And I will show you. The simple case is, even if you have a single user, you have a button that submits something. The user can click multiple times without being aware. It's very easy. It's just double clicks, and then there's absolutely no guarantee which of these requests will come first. Actually, it depends on a lot of conditions, and they can just come simultaneously. So it's possible you can break your database just by you can create concurrency even if you have one user. Well, I can disable the button, right? But then a malicious user can just, or someone curious can just go to your HTML and then undisable it if they want to. You can say, well, I trust my users. We're a small company. Then perhaps you use some services that does the traffic, and then, well, there's a good chance that that service also may issue a concurrent request for the same thing, same entity. It's quite possible. You would say it's rare, but you may end up with this kind of issues. Yeah, it's pretty rare, but once you end up it could be pretty bad actually. Another example. So once we learn about transactions, right? I don't know, maybe school or something like that. The classic example of a database transaction, a space compliant transaction, is that, let's say you want to transfer money from one account to another, and you need to do both actions, deducing the money and adding the money in the single transaction boundary. That way, it guarantees that nothing can go wrong, because if there's an error during any part of the transaction, it will roll back and then it will preserve the existing state. Otherwise, the database will make sure that it will just commit both sides at the same time. And how you would code this, just for example, let's say you are not allowed to withdraw money more than you have. You check the balance. If it's available, then update, right? But to handle the concurrency, then you just need to, let's say, if 2 or more transactions trying to achieve access to the same account, then you need to use some sorts of locking mechanism or a pessimistic or optimistic concurrency mechanism. Let's just study that. So in this case, we have 2 transactions, and they're simultaneously transferring money from account 1 to account 2. And what they do is, what transactions they check, if there's a, let's say initially account 1 has $1,000, and then account 2 has $0. And what they do is simultaneously they check if account 1 has enough balance. Because we have transaction isolation, each transaction can only see, I mean, they behave as if they are the only thing they're running, right? They can't see the other transaction. And they both say, yes, there's enough money. and then they will both update the account 1 to 0, and then they will both update to account 2 to 1,000. Or if they increment, then they will have $2,000. Who knows? So it's something very, very unusual can go wrong. It's very easy, and the only way to tackle this problem is that in a classical sense, you either lock the rows by using pessimistic concurrency. Most databases allow you to lock the rows or serialize so you can serialize the transaction, but that's not very scalable. If you lock the row, then you're actually doing something very bad. I don't recommend you, and because the deadlock is very possible, even small amount of rows. The deadlock happens if two transactions happen to read rows in opposite order. So let's say there's one transaction is sorting the accounts from A to Z, and the other transaction is trying to access in a sorted way Z to A, and then perhaps transaction A locked A and transaction B has locked B, and then whenever transaction A tries to access account B, it's locked by transaction B, whereas the same thing vice versa. You could also use optimistic concurrency, which is more popular. In optimistic concurrency, you add a version or timestamp column to your table, and then each time you update, you check if you put a where condition to your update statement, checking the version is if it matches or not. Then again, just like David Fowler did, you check the updated records, and if it's not what you expect, then it means there's some problem, some concurrence problem. Then you need to restart your transaction to recover. However, what if you had issued some side effects? What if you sent and make web service calls? So you can't just easily restart the transaction. You have to think about it. There's no proper solution to this problem, even with the CQRS style, but it's not something you can naively apply. I'm referring to the optimistic concurrency. You have to think about these kind of effects. So what do I suggest as a solution? It's a lot of chatty thinking, actually, and it's somewhat difficult. So actually, this is somewhat the domain-driven design dictates. You have to have invariance. An invariant is something that can never change. In our case, an account can never have a negative balance. Notice, I didn't talk about two accounts. I say an account can never have negative balance. That means my invariant is associated with a single entity. And that means transaction boundary must be associated with a single entity. It's invalid to involve multiple entities in a single transaction. Then how am I going to transact money? What if something goes wrong? I was comforted by the database's mechanism, which could just handle this thing. Well, you have to end up with a transaction coordinator by yourself, which is something like a third entity, and you issue the request to that. And if you're familiar with two-phase commit, so it will apply poor man's two-phase commit. It will say, well, account 1, do you have enough money? Someone wants to transfer money. Account 1 will say, yes, I'm reserving for you, but not deducing yet. Then account 2, are you ready to accept money? Account 2 will say, yes, I'm ready to accept money. So if both accounts says yes for voted, the transaction coordinator will record this answer. And then it will say, okay, account 1, reduce the money, then it will reduce the money, and account 2 get the money, and then it will increase the amount. If anytime this process crashes or something like that, then the transaction coordinator needs to restart and ask these questions and replay. Hey, account, can you reserve the money? It will say, I already reserved it. That's fine. And then it will continue. So as you would notice, if you go with that, at some point, there's some point in time where the account 1 has lost its money, whereas account 2 did not yet receive. And that's why we have eventual consistency. It means the system may not be consistent at some point, but eventually it will be. So that's a little bit scary. But let's just see a little bit more in sequence diagram. This is a little bit old edition. Probably I wouldn't do it this way, but it's something less perhaps valuable. So you want to transfer money, you get to the command handler actor. In this case, it says, which I will talk what's an actor, don't mind it. It says the source actor transfer money. It says the amount is reserved. There is some sort of transfer process going on. Once transfer process receives the event, then it will issue a command. So every blue arrow is an event here. Every red arrow represents a command here. Where once the target actor also receives the command, it just says in the 5th step, amount reserved. In the 6th step, we confirm. We get in the 7th step, we confirmation. And the 8th step, we confirm. And the 9th step, we get another confirmation. We are done. That's a little bit chatty. So it's pretty hard to convince someone who get used to the old style. Hey, look, you're doing wrong. This is the correct way. But to be honest, this is the correct way, whether you like it or not. So this is somewhat correlated with the source of truth. This is a little philosophical concept. What is the source of truth of your application? 99% of people's applications, it would be the database. And database is something that's very vendor locked. You use Oracle, PostgreSQL, whatever, SQL Server, SQLite. It's an implementation detail. And personally, it bothers me a lot to rely on something very a vendor to that, because every database has different facility, different features. Some of them can do some things, some of them are not. And also they are not objects. So we like to even you're doing OOP or something like that. Then you realize your ORMs are just joke. You're trying to model architecture or nice objects. They're just hydrated when a request comes and dehydrated. Dehydrated when it's just request finishes. And your database becomes also bottleneck. If there's a lot of traffic, then everything you can scale your web front end as much, 10 pieces, 20 pieces, yes, but you need to resort techniques like sharding, etc. for your database. It's just become the source of truth. Can we move the source of truth to your application and let database be the database that store data, not being source of truth? That's where actors came in. I'll start with actors. So an actor is actually, if you're familiar with objects, they're very similar. An object in OOP sense is something that holds the state, optionally, of course, and then also it has some behavior through methods you can invoke. An actor has exactly the same characteristics. It also holds a state, some sort of state, and also it receives, instead of methods, you just send a message. Then it reacts. But there are some characteristic differences between an object and an actor. Well, first of all, usually when you call a method of an object, the method has to return, whether you return void or something like that. Whereas an actor, there is no such thing. You just send a message and that's it. That's it. An actor has a capability to return out of bound messages, responses. So it can return multiple messages with something 1 hour later, etc. If you look at it, it's actually more alive, more reactive. That's why we call reactive programming, because just like radioactive elements, which they can react at some time, then they can split, right? They're on their half-lives. The actor can just also react after some time, even if you didn't invoke it. Another big difference is just an object is just a pile of memory in a fixed memory location. Well, there's garbage collector can move the object, but it's still, after the movement, it's still fixed to a memory location. Whereas an actor is more abstract concept. It's not bound to any memory location. It's something, even it is possible you cannot know, in which machine it is. It is something like a real entity, and in what memory location it is, and in which server it is just an implementation detail, which you don't care. In that sense, actors offer a greater abstraction over objects. This screenshot you see, it shows the Akka.NET lifecycle, which says that, well, something crashes, it can restart itself, etc., etc., which I'm not going to talk about detail, but I'm just trying to emphasize its detail, its differences detail. But actors are like atoms. So what can you do with actors? Actually, by itself, it's not. When I read through Akka.NET, interesting, but why do I use it? I couldn't find any use case. Well, the use case is like actually you realize the actors are like a Lego, and they become useful when you actually build something with it. They're not by itself so much useful. In some sense, by a naked actor is similar to a mailbox processor or an agent in F#. But once you facilitate with some additional stuff, here I'll talk about a gossip protocol. Well, these A, B, C are physical machines, different nodes, and then you can connect them through the network. And even if, for example, at some point later time, B didn't know nothing about C, let's say you have hundreds of nodes, they will be acquainted to each other by gossiping, because under the hood network will tell, or hey, tell about the network infrastructure. And whenever you need to send a message from B to C, you don't have to know about its IP address or even the domain name. You just know it's the actor name, and then you can just publish a message, and this cluster will deliver the message to the correct place. Further, gracefully or ungracefully, if you take one of these machines down or it just crashes, then it also lets the cluster know about that thing happen. It will say, well, if B crashes, eventually, not instantly, but eventually, the C will be aware the cluster is going down. And if you make it gracefully, like you have a Kubernetes cluster or something like that, and if it, let's say you're doing a blue-green deployment or something like that, then when you take B down, the system is smart enough to find out, hey, I'm about to deliver a message to the B, but I'm not going to do that because it's just going down. I will buffer it and I will deliver it once it's up. So it can do this automatically for you. Or let's say you already delivered the message and you're trying to gracefully instruct the B to down. The B will wait to drain all the messages. So you're not going to cut the user's request in half. So it's augmented. An actor system is augmented with a lot of different facilities in a distributed environment. Okay, I am not doing distributed programming. I'm about to develop a single web page in a single machine. I still use this system. Let me tell you why. So in a sense, it actually abstracts the entity. So you can just make a single cluster, single node cluster, and then you say, I want to listen port 0, and then if one of the nodes go again, I'm talking about multiple nodes, but let's just revisit the single case as well. If one of the nodes goes down gracefully, what will we do? Let's say there's a shards here. You can also do sharding here. The system will transfer those entities gracefully to other shards. So then you're never actually down. The system will continue. But again, as I stated, Akka cluster sharding actually helps you to deal with entities. When you talk about entities and Akka, then actually you need to go with cluster sharding, because that concept introduces entity, even if you have a single web application, and it's not complicated to set it up. So as I stated, the actor system is just it's about sending a message to something, some target. And this message in the case of cluster sharding involves 3 parameters: shard ID, an entity ID, and the message. Shard ID can be something fixed. You can say, if you have a single web application, you can just say 1 or A, whatever. You don't have to change that. But you can also, if you want to scale your application, you can just make it a programmatic logic that defines the shard ID. Whereas the entity ID is the user, for example, could be a username or bank account name. And the message is just the message you want to send. It could be a complex object. So in the last line, you can see this region tell. The interesting bit about this thing is if you have multiple cluster, you don't have to know where that entity is. It will find out and deliver the message. Even if you have a single cluster, let's say this entity has never been created. You're not sure if it is there or not. Maybe no one has created entity 1, right? it will create it for you as if it's there. So it's more like the object creation is transparent to you. So you don't have to worry about is the object there or not? Should I create it? Nope. It will initialize the actor for you if it is not there. And if it is there, it will deliver the message. So let's say let's just present an actor in that sense. So I talked about CQRS. You deliver a command, and there's a command handler. It just issues an event. So the regular entity actors are something like that. Just accepts a command, and they publish an event, and they also persist those events. In this case, I want to log in. Maybe my password and the Norway is my shard ID. Okay, I'm from Norway, my location, and owner is my username. And I also deliver the password, etc. And then the user actually receives this command message as a message. It checks my password, etc., etc., and then decides on whether I logged in succeed or not. Then someone is listening, and then we'll check it through, which we'll talk a little more through. Okay, I'm here. Just my headphone paused for a while. Now there's some concept called saga. This is actually terminologically wrong, but saga is something else terminologically. It's for the service bus stuff, etc. But I'll use it in their different context, which calls process manager. So earlier, if you recall, in an earlier slide, I talked about distributed coordinators, where I said you are not allowed to initiate a transaction between multiple entities. And a saga is like a process manager, where it actually can deal with coordination between multiple entities or multiple services. So you're not allowed to, in this design model, you're not allowed to send a message from an entity to another. Well, Akka allows it, but I recommend against that. And let's say you have the event successful. In my own model, I declare a global single actor through a single node per node. It's called Saga Starter, and it listens all the events in the system, and then perhaps it optionally decides it should start a saga or not. Not all events will start a saga. For me, for an event to start a saga, it should have an involvement with an external service or another entity. If that event doesn't have any interaction with another entity or another service, then I don't start a saga. If it does, I do. And what I do is, after the event is published, I make the original actor penned, even not persist a single message yet. I first start the saga. The saga records itself to the database, say I got started, and then issues a continue message in night step 4. And only then, after then, it actually has the original user actor continues. Let's start a little more chatty, scary. It's a little more complete and concrete implementation of money transfer. Probably this is how I would implement it today. But there are a lot of arrows, and again, it looks scary. But actually, if you look at a single circle each individual time, at least the entities are somewhat, they're only taking a couple of commands. So let's start with item 1. You have a web application. You issue a command, let's say transfer money. That causes a transaction entity to start. Akka will initialize it for us, even if it is not there. And then it will evaluate the transfer money. If it is valid, it will issue in step 2 a transaction started event. The saga starter will receive that event, and then it will, in this case, start a saga. In step 3, it will issue a command to a non-existent entity. Saga is also comes about entity. In the step 4, saga says, okay, I started. And once it's doing that, it will record itself and the started event in step 4 into database. In step 5, saga starter says, okay, continue. We started your saga. Step 6, now we'll reissue the message. Now we are going to full scale CQRS with actors. It will reissue the event. The blue icons, the blue arrows are events, and the red arrows are commands. It will say transaction started. Okay. Now transaction started message contains the transaction details such as the accounts, amounts, etc. It knows the account IDs. The transaction saga will coordinate the two accounts. So it will go to in the step 7. It will tell account sender reserve an amount. Step 8, amount reserved. Okay. Go to step 9, reserve amount, perhaps in a positive way. And then step 10, okay, amount reserved. And then we'll go to step 11. Okay, we got both votes yes. Step 11 says complete. And then step 12 says, okay, complete it. And it will reduce the amount of money. In step 13, it will also complete, and 14 is just completed similarly. And then both accounts, both actors have done their transaction, and they are the source of truth. They have the actual state of the system, not the database. They are alive there. Once both sides complete, we go to step 15. We say transaction saga, okay, done, completed. And then transaction entity itself will return an event, publish an event called transaction successful. And the web application is pending at that time, waiting for this event to happen, and it will return the user, you're done. Now the scary bit is this. What if the system crashes at any point of time? The transaction saga, it's actually very simple to deal with this problem. The transaction saga has only have to know what was the last number that was sent. It has to record it as a state machine. So if it's 7 and the system crashed, it will reissue the 7th command, reserve amount, with the associated transaction ID. And that should be idempotent. The account sender will check the reserved amount ID. There's a correlation ID I used. If it's already reserved, it will still send the amount reserved. Or maybe you can just say amount already reserved if you want to distinguish between these things. Then it will just do nothing. If the amount has not even yet reserved, it will do the processing. And then transaction saga will continue. Challenge 2. How the system will know that there was a transaction in the first place? My system crashed and I restarted it. Right? How these things will come up again in the original state? There's a facility called in Akka called remember entities. And I decorate the saga entities, only the saga entities, as remember entities. That means whenever the actor system starts, it also restarts those sagas if they are active. If they are not completed, which you can mark them complete, and it's not going to start. So that way, if at any point if the system crashes and restarts, the transaction saga will come to alive. The other actors are not alive yet. And then it will issue those messages and make them alive. Challenge 2. If every transaction, I create these actors, will I not go out of memory? Do I not need something like some sort of garbage collector? Yes, you do, and that's correct. Well, my guess is, and each actor occupies around a kilobyte of memory. So they are not very heavy, and they handle the threading very efficiently. But there's another setting in Akka.NET where you can say passivation timeout. The sagas never passivate, by the way, but the other actors, like entities, you can configure, which is by default 2 minutes. If they don't receive any message by 2 minutes, they will just passivate themselves, take themselves out of memory. But they do it such a way, it's very graceful. Let's say, again, as I stated, there's a message on the way. It will either tell the sender to buffer that message, or it will cease passivation. So it will make this passivation in a way, even if it's concurrently dense, it's not going to lose it. It will not passivate. It will cancel the passivation, or it will passivate, reactivate, etc. Find a way. It will most definitely handle the message. So in that sense, it's actually Akka is very, very, very robust in that sense. So if I were to recap this, I talked a lot on the slide. We have entities which take command and emit events. We have sagas which take events but emit commands, so they're mirror image. We have a saga starter where they take the events and decide if a saga should start it. Sagas are called, we configure as remember entities in Akka.NET so that whenever entire system crashes on restart, they automatically restart. What Saga does, it bookkeeps the number. What was the last event, or sorry, what was the last command, and then it just reissues those commands on a restart. And then basically it coordinates the transaction between multiple entities here. So that's the essence of Sagas. So it was a lengthy talk, but that was the essence. Then there's this the setting in Akka.NET, which is by default 120, which I'm not going to talk about it. Yeah, so I just talked about remember entities. How do I initialize an actor? So this is the how part. Now we talked about it, a lot of theory. So the basic essence is I like to use, so Akka.NET has its own Akka F# kind of stuff, which you can use, but I like to use Acklink, which is a very tiny wrapper over Akka. If you create an FSX file, this is all the code you need. There's nothing else is required. You don't even have to install a NuGet package or something like that because we just have this R it will install. But Akka serialization Hyperion perhaps is not required even here. I think it's just the serializer. And Acklink is the Akka wrapper. So if you're familiar with mailbox processors, you will see it's very close behavior. It you just have this actor computation expression. M.receive will say it will pend here until it receives a message. Once it receives a message, we just do pattern matching, and then we decide. So we can return special messages such as stop and unhandled, which returns a stops the actor. Unhandled says just I handle, and it's logged into an error log. Whereas any other kind of this thing it will print. And you see there's a recursion here. If you're familiar with mailbox processor, it's the same. The state of the actor here is the unit here. So you just whatever passed to this loop parameter, it will be your actor's state in memory. And actors are in this case it's spawned via spawn anonymous function, which is something like Acklink's nice thing. You pass the system, and there's a props function. You pass the behavior, and you get an hello ref as the actor. And by default, actors are type safe. So so this weird operator with a smaller than and then bang, it will accept a string. However, I would suggest if you try to go with CQRS style thing with persistent actors, you just stick to objects because there are very different kind of messages. So speaking of persistence, so this is the second kind of actor. It's a little bit more enhanced. And how are we persisting the messages? So I talked about persistence, but how are we going to do that? It's the same thing. We create a system. The system the name can be anything. Well, there's an event called counterchanged, which issues a delta. There's a commands. You can increment, get state. I would advise against anything like get state or that returns state. Don't do that. It's against CQRS. Then a counter message can be either an event of command or just a command or event. So it accepts both of these messages. He did that because of type safety. Whereas in my case, I just stick to objects. It's a futile attempt to make things type safe when you go full-blown CQRS. But anyway, so at below you can see it issued the two increment messages and then a decrement message, and then it just gets the state. So whenever you issue a command, it will the mailbox processor will receive the message. It will match the command. In this case, it will start with increment. Notice it says return persist. So it says I like to emit an event and I want to persist it. The next thing will happen is it will come when you persist it. It will come to this event loop, and then it will change the state as delta. Whereas with the decrement, it does the same thing. And each time this loop executes, it will insert a line into a log database. That what happened in the system. Notice simultaneously we are also updating the state in the memory. But if this actor crashes and restarts, what will happen is it will replay all these events from the database, right? And then it will just come to its original state. And notice, just like mailbox processor, actors are thread safe. You don't have to worry about thread safety. An actor can only process one message at a time. The other messages, if they come, they will just pend in some sort of mailbox, so some sort of stack kind of thing. So you're not going to have any concurrency issue, even if you want it. Alcanet supports variety of persistence. I use SQLite, Oracle. I think MongoDB is very well supported. Yeah, so SQL Server, I used it also. And there are other ones as well, Cassandra, and I don't know. You can just Google it and get. So when it comes to cluster sharding, the ACLink syntax is slightly different, where you would just create a cluster system, etc. And then at some point, you create the entities by entity, something that you can send. You're not creating the entity, but you're creating an entity reference with this fac ref4 shard1 and entity. So it just gives you something, a factory actually. Then if you issue a message to this factory, then it will create an actor for you. Now this is how the cluster sharding works. Whenever you facilitate there's a recipe I came up. Whenever a command comes, you first validate. Then you create an instance. Let's say transfer money. Okay, I will transfer it. There's enough balance. So second event, this amount is deduced. Then you apply this event. You just loop through this recursion and then change the amount. You persist the event. Step 3 and 4 are interchangeable. And published event, which we want to know the system that something has happened. So that's the recipe I follow. So I'll talk about something, but I'll just stop here briefly. Do you have any questions? It was a bit dense. If you're hearing for the first time, it's finished. Yeah, please go ahead, Hadi.
Yeah, I want to go a little bit before to the very beginning. Speaking of CQRS and having akka as well.
Yes.
So I'm coming from a .NET background, and generally for CQRS we use like a library called Mediator.
Yes.
I was thinking now that akka is in place, and this is a decision I had to think about. Would you actually just like use both together, or would you say, okay, my actor now is my, for example, command or a query handler, so this acts as a part where actually get replaced altogether by a mediator or any other library?
Well, my exposure with Mediator is little, but I'm well aware of it for years. It's very popular. I think it offers you a built-in architecture, so you don't have to think about these intrinsicies. But this is not what I'm talking about is not a framework or library. It's a pattern I came up. So you can just modify it. So my answer would be, so if you look at this slide, you could just pick. So a good practice is about separating your application into vertical slices, bounded contexts. Maybe there's an authentication system, subsystem. Maybe there's a transaction. So I can't answer that to you. I'm very well satisfied with this, but it's there's also if you're familiar, if you're not familiar, you will encounter some corner cases, etc. So it's better to ramp up and try in a smaller, non-risky bounded context.
If I phrase the question differently a little bit, let's say the command handlers. What would be your command handlers from akka point of view, for example?
There won't be actually.
There won't be. Okay.
No, because when I use, I will show a little bit more real life code briefly. But basically, I have some sort of helper utility, but it's not an actor per se itself. Because once you use cluster sharding, okay, you can just get the command as a message and then deliver the target directly through sharding, and then the sharding system will create the actor if it doesn't exist. So the sharding system somehow takes responsibility of this command handler mechanism transparently. Yeah. So that would be my answer, which I will show some sample code.
Sure. Yeah, we can take a look at it later.
Yeah. And that is actually where I came from. So So there's some side project on mine, which I will show you. It's something I'm proud of, but trying to commercialize, but there's nothing concrete yet. It's called bindrake.com. What it does is it actually it's a 3D bin packer. So if you have a container, you want to put some boxes into that, then it allows you to fulfill that boxes. And has some sort of, this is not relevant. It has also some sort of, I'm trying to sell credits to people where you want to purchase credit. I integrate with Stripe and you pay with money with your credit card, and then I just issue a credit card message. Whenever you execute something, I call this consume credit. There's also the login, for example. Whenever you log in, you can. So it's still a little bit on the fly. I can't say it's perfect, but I think it's somewhat decent. And then you can see at the top of the commands, and the events is just outcome. So usually events have two pairs because usually they can succeed or fail. In this case, I didn't put credit edit can fail because I can't think of a case where it would fail, but the other cases might fail. Let me show you the web app. It's not the interesting part. It's written fully in F#, just if you're curious. So there's this container. You can just put some sort of dimensions. Then you can just say, I want to fill a box like 3, let's say make it 4, more interesting. And then you click calculate. Hopefully I'm still alive. I did not log out. And then it will calculate how this box is going to go. And then, yeah, it'll take some time. And then it demonstrates it in 3D way that you can, how you can, so it makes a 3D bin packing algorithm over that. Then once you do that, it just reduces your credit actually. And you click that, you can buy credit, you can log in, log out, and that's all about it. So basically you can add more items, etc., etc. So I'll just describe, so this front end isn't very secret. Of course, the algorithm belong to me, it's secret, but I'll just share some parts of the code, how this works. And this is fully working on this in this methodology, and it's still alive now. You can just use it in bindrake.com. If you have, if you're in cargo and packing business and e-commerce, ping me. I'll just help you out. If you have packing problems, let's solve it. Anyway, let's just yeah, actually, let's go through the source code in a better way, so that you can just, because seeing is believing. So in my project, well, there's this client which is this Fable. I like Fable lit web components. Some people who know me know about that. There's a domain part. For me, the domain is something. It's a little bit misused name. It represents the API surface actually. So it's something that's shared between the backend and the front end. But I like to keep this domain because actually I like something called API first approach. And API first means actually this is what you care. In the API first, there's some sort of nouns, some sort of credit, etc. There's some sort of commands, but you can log in, verify. So it's just definitions of this type information. There's something called query. In my UI, I only query get credit, and then well, it just credits. So the MVU is the Fables backend. It's not that important. So it just uses pure Elmish, still front end stuff. And the server is just Giraffe here. So what Giraffe does is, just if you're familiar with Giraffe, it serves as some sort of set of handlers. Let's just look at the what handler? Look at default. So well, so there's some sort of it calls my backend service. There's another backend service of this thing, and then once you, so before you call, it actually calls a function. So this is still ASP.NET world. And yeah, so there is an environment variable. I pick it up. It's just like an interface injection. And let's say this is a consume credit function. So this is just a regular interface. There's nothing CQRS related stuff. And I just issue a command. And that command is somehow, which I will skip those details, land into some implementation. There's an interface here, something like, for example, it lands here. So there's some sort of wrapper here. I wrap my command, some sort of decorate with details. There's this correlation ID, blah, blah, a lot of stuff. So this is an implementation detail. But what I do is important and logical. I'll just describe verbally. I will, before sending the command to the system, I haven't still sent yet. I'm still there. I will subscribe for the outcomes. In this case, I will subscribe for the credit consumed. So if the credit consumed or credit consumed failed messages comes, you see the subscription, then it means the ASP.NET side is just can continue. It will indefinitely wait, block here, because this match bang here, until that response comes out. Okay. Then depending on the outcome, I can just say, well, if you don't have any credit, then perhaps, well, it's a bit abstract. There could be many reasons you failed, but I was lazy. I assume you don't have any credits, or I will just return a version. Version is something important. In my case, every actor, every entity, every state has something called version. It's a number, an interesting number, which I will talk about briefly. How this subscription works? Well, there's something called there's a public version of this code somewhere in my repo. But there's some, as I said, this is not a framework yet; it's a pattern. But I have a common stuff which I copy to paste to every project I had, and then every time you want to subscribe, I create a generic actor, and then it listens through. Akka has some built-in event pops-up system in a distributed way even. So it subscribes to this type, and then it actually subscribes per the correlation ID. And then whenever a message comes with correlation ID, it checks that if this message is relevant or not. And once it's relevant, it will return. Otherwise, it will ignore the message. Yeah, so that way it subscribes. So we haven't still talked about the actor system much. Let me just find the API. Once we have it, this thing will issue this message that, for example, you add credit or remove credit. Now let's see the actual actor here. So in my case, in my domain model, this is, so for each actor, I create a module, and you can see, so the first thing I do, well, this is the default chart, not relevant. I create a set of commands and a set of events. And then, so these are some boilerplate code. This function is the outside of the actor. It just changes the state. So whenever I get an event and my state, it's just the event handler actually. It changes the state. Whereas with the actor, this actor starts here. There's some built-in lifecycle functions. It's not relevant to my model, but it's for example, whenever a message is persisted, I want to apply. Whenever the state is playing, from whenever this actor system is restarted, this actor initialized, it will apply again. There's also some sort of snapshotting. Snapshotting is like if you have 1 million events, you don't want to replay them. Just replace them, etc. So you can see that. Anyway, there's some other details. Yeah, and so this is the command handling mechanism. So the message will come here. For example, if you add a credit, it will issue a credit added message. If you try to consume a credit, well, it will check if this amount is sufficient, that you have enough credit. Depending on the outcome, it will issue this one of these messages, and then it publishes events to the Saga. If in this case there is not related. So that's the publishing part. And then what happens is each time it's persisted, you will see one statement in the log. Whereas with the query side, if you go to here, in my case, I used a SQL provider, which is actually very challenging. I'm running on an Apple Silicon, and Docker. This is a Docker container. You need to grab some binaries. In this case, I had to grab Linux ARM binaries. That's somewhere here. Oh, anyway, that's not relevant. What's relevant is for the read side, Akka also has something called Akka streams. And then it will actually, I think it's here. So the source. Yeah, so this is configuration. How does it know the database? If there's a configuration. So basically I say there's an offset count. each time I commit changes, I just update this. So it will start streaming from this source, and for each event, it will push it to the handle event wrapper, and then it will continue this forever until the system crashes. And then the event handler is just getting each event and create a relevant database record. So for example, if you consume a credit, let me find it for you. So you can see it actually deducts the amount of that from that user. So this version thing is every time an entity is modified, it will update the version. This way, because there's an asynchronicity with the read side, from my command side, I always return the version. So that the query side can always try a version that is greater than that. Let me just find, there's a retry function somewhere. Retry. So you can see, well, there's a retry function. Whenever this is Fable, by the way, client side, and it just, well, it's a little bit hard coded, but it tries exponentially, tries to get a version. Let's just go to the actual definition here in the in the server side. Greater. So I come up with this kind of manual mechanism, but let me find the relevant codes here. Greater or equal. Can I find? No, this is 3JS. Fable validation not relevant. Model not relevant. The API is not relevant. Yeah, for example, get credit. It basically says, well, find the credit data is equal to the user value should be equal to this user, and the version must be equal or greater than the version that's returned. That way, it ensures to get the correct data. Yeah, actually, I have some limited time, and the remaining slides are just going through the same thing. Actually, there's a couple of slides. So how do tables look like? So you can see on the left pane, I'll try to zoom. These are a set of events here. There's a payload here. The event is serialized by JavaScript. For serialization, you have to be careful about versioning. I use tot, but you can use a different serializer. And I spoke to read side. So every time you need to update the offset count in same transaction, so that if the system crashes, it can replace successfully. And then this is the offset table, and this is for example, the user table. That's the final projection table, how it looks like. There's a website called, there's an older version of this library is available in the framework. It's called Language Planner. So here you can see it also allows you to subscribe to live events from your web application. This is through WebSocket, of course. But anyway, so that's all I'm going to talk about. It was very dense, and I doubt at first sight you'll be even convinced, let alone to apply. But my objective was to create awareness of such a thing exists in the first place. And it requires some bravery to go through this. But I feel like despite a lot of complexities, it feels like the silver bullet of domain-driven design and web development. Thank you for listening. I took a little bit more time than I should. If you have any questions, now it's a good time. Other than that, you can just send me a message through this meetup or Twitter, if you have my Twitter. I guess no questions. I'll post the, so I'll publish this recording to YouTube. Yeah, Mayor.
I'm sorry. I was just going to say, will the slides be available in your?
Yeah, that's a good suggestion. I'll add it to the meetup, so you could.
Thank you so much.
Yeah. Also, as I stated, the YouTube will be. Yeah, so I'll publish to YouTube. Also, the link to the presentation will be published to the meetup. So in particular, this event, I'll add this link so you can rewatch it. I know it's dense. Sometimes.
Sorry, I do actually have a question on distributed programming in general. It's not related to akka. It's something that we're considering too at our company. If I'm using an API to perform an action or run a command, as you say, from the user's perspective, I'm waiting for a result. But in the backend, the code might be running in a distributed fashion. So what sort of techniques have you used to convert that asynchronous to a synchronous style run and wait for the response?
Yeah, you have some options such as, I'm not sure what I mean, it doesn't have to be distributancy here. But let's say sometimes you have to have a task that runs 1 hour and you don't want to, in particular, for example, if you try a regular HTTP request and Azure will kick you out after 3.5 minutes.
Well, so what I mean by distributed and going into the Akka world now. So you could have actors that are running on different machines, say, and those actors they're all performing the task of that API action endpoint. So at some point within that distributed sort of cycle, the API needs to know that, okay, now my work has finished. This is the final response, and you can now reply back to the consumer that the action is done, and here's the response.
Well, one way is the way I did. So you can just create a WebSocket and subscribe here, just like I did. One way. Second way is do polling.
Yeah.
Okay. So if I were to do, if you ask me how would I do it? Well, it depends. So I would refrain. I could go with sockets, but also I could go with the polling to read side of table. So let's say if I do CQRS, which is not relevant to your question, I know, but also let's say I have a distributed calculation, it just does a lot of things and I'm waiting for the result. So all these actors can eventually will generate a result, an outcome, that distribution, right? And that result will be available somewhere. It could be stored in a database, or if it's a mere calculation, you can just publish it. Okay. Then from your web application, you need to either poll where it is published or subscribe.
Okay, yeah, that makes sense. It's a similar pattern that's followed in durable functions, right? With Azure's with the whole orchestration.
I guess. I mean, this is not a problem it's just some sort of long computation. So waiting for as I stated, you have a distributed system. Eventually, you need to converge those distributed systems outcome into a response. Or you can just, each portion of your distributed system can publish events. Let's say maybe you want to see the progress. For example, you have a distributed system, some part calculates one thing and the other one calculates another thing. And then you want to get notifications of steps that's done. Then each of your parts can just send a message, and then you need to poll through something, or through WebSocket you can subscribe. That's what I would do.
All right.
Thank you for joining. It was good to talk to you. I hope it was beneficial to you to a degree, at least. Then see you next time.
Thank you very much.
Thank you for the talk. Perfect. Bye.